Good morning. So I want to continue our discussion of Chapter 4 today on the course of reactions. And what I want to talk about today is the effects of activation energies and temperatures on reaction rates. And I want to introduce an equation that I find very useful. It's called the Eyring Equation. We're just going to go through sort of a light derivation of it. It comes from transition state theory. But I want to show you how to use this equation to look at how temperature and activation energies control reaction rates. And we'll take a couple of different examples from a reaction that's going to be in the homework problem in Chapter 4 and some examples of things that I think about in NMR Spectroscopy. So let's begin. Okay, so we're just going to keep it simple, we'll just look at a unimolecular process. So, okay, in a unimolecular process, or in some reaction, we'll treat it as a unimolecular process. We have, reactants. I can't talk and write at the same time. Reactants go to products, right? This is what we've been talking about for the past couple of days, past couple of lectures. And there's some rate constant K. And if we're dealing with a unimolecular process, and I want to sketch out a reaction-free energy diagram, we plot, as we've done before, free energy on the y-axis. We plot our reaction coordinate on the x-axis. And for some fundamental process, like say an SN1 reaction, actually what I'm really talking about, I guess, is a single step. So let's say the first step in an SN1 reaction, the ionization to form a carbocation, or an SN2 process where the reactants are coming together. But for a single step, where we call the products whatever you've formed, we're going to go from reactants to products. And I'm just going to write this for a downhill reaction, for a downhill exothermic reaction, exergonic reaction. We go over an energy barrier, the transition state, like so. And for that step, and if it's the whole reaction for that reaction, you have a free energy of activation, delta G, double dagger, which is the difference in energy between the energy of the transition state and the energy of the reactants. All right, I'd like us, in order to develop this equation that's going to allow us to relate reaction rate to temperature and energy barriers, I'd like us to conceptualize this reaction occurring in a process by which we have a pre-equilibrium. So, right, if we just write it for this reaction, we can say rate equals rate constant times concentration of reactants. And what I'd like to do is to slice and dice this a little bit finer to conceptualize this as having a pre-equilibrium, where reactants are in a pre-equilibrium K, pre-equilibrium with the transition state K, with an equilibrium constant K, capital K we used for equilibrium constant, lowercase k we use for the rate constant. And since we're going to go ahead and talk about the transition state, I'll call that K delta dagger for this conceptualization of this pre-equilibrium. Remember, the transition state isn't a species you can put in a bottle by any means. Unlike a carbocation, which is in an energy well, the transition state doesn't exist for a millisecond or a microsecond. The transition state is this fleeting instant, this bond vibration, this femtosecond lifetime, not even a stable species, just this point you pass through on the way over that energy barrier. So let's conceptualize this as an equilibrium where you form the transition state and then say, okay, the transition state goes on with some rate constant K double dagger onto our products. If you want to conceptualize things this way, remember for the fundamental step, then we'd say our rate is equal to K double dagger times the concentration of transition state and of course we don't know what the concentration of transition state is. But if you think of that as an equilibrium, the concentration of transition state divided by the concentration of reactants is equilibrium constant K double dagger. So we get rate equals K double dagger, lowercase k double dagger, capital K double dagger, times concentration of reactants. Now, if that looks weird, all I've done is diced and sliced this familiar equation, rate for a fundamental step equals K, the rate constant that you observed, times concentration of reactants. All I've done is dice and slice that K into K double dagger equilibrium constant. Now, what I want to show you is the implications of that. So, you know, if you're studying organic chemistry, we don't have to think about a lot of equations in organic chemistry. In fact, I'll say there are two equations that are mathematical equations in organic chemistry. The only thing you really need to know in organic chemistry is delta G equals delta H minus T delta S, and delta G equals negative RT natural log of K. I'm writing really sloppily today, my apologies. Delta G equals negative RT natural log of KEQ. If you know these two equations here, you probably can do most of the math in sophomore organic chemistry. Freshman chemistry is a different deal. There's a lot of mathematics there. By the time we get to sophomore organic chemistry, we forget most of that math. This really becomes maybe the only thing that's really important, as long as we maybe on top of that remember that our equilibrium constant K for a reaction is the concentration of products, you know, whatever, to whatever power they appear, over the concentration of reactants, right? So that's everything you need to know to be a sophomore. Of course, you need to know functional groups, you need to know curved arrows, you need to understand reaction mechanisms, you need to understand stereochemistry, but that's what we take away from general chemistry. So today I want to give you one more equation that I think, right, we're in an advanced course, one more equation that I think is really powerful. I want to take you through sort of a baby derivation. All right, so if you take this equation, of course, you get that K equals E to the negative delta G over RT, right? That's simple math. That's just the corollary to this equation. K equals delta G negative RT negative, okay, for equilibrium constant. So the one dice and slice I want to put on that now is come back to this pre-equilibrium for the formation of the transition state, where we treated this as having an equilibrium constant K double dagger, capital K double dagger. So I'll go ahead and I'll add that. So that's our basic from delta G equals delta H minus T delta S. Delta K is equal to negative delta G double dagger, E to the negative delta G double dagger over RT. All right, now I want to throw one thing at you that we're not going to deal with any sort of derivation on, And that is the rate constant K double dagger is equal to K Boltzmann times temperature over Planck's constant. And this comes from statistical thermodynamics. K Boltzmann, Planck's constant H. So if we take that, okay with that? And if you've had physical chemistry, you've probably got something like that. But we're just going to take that. You hated it?
We're in there now.
You're in it right now. All right, well, I'm an organic chemist, so I'm much more simple-minded about things than a physical chemist. You got to be smart to be a physical chemist. We're doing what's called physical organic chemistry, by the way. This is understanding reaction mechanisms. This chapter 4 is actually packing in a lot, because we're doing two things in chapter 4. One is an introduction to physical organic chemistry, how reactions occur. The other is a refresher of curved arrow mechanisms and other mechanisms. So the homework set that we have in chapter 4 has sort of 5 problems on physical organic chemistry and 5 problems on reaction mechanisms. And I'll tie our first example to one of those problems on reaction mechanisms. I've also put a hint on that. All right, if we combine our K double dagger from statistical thermodynamics and our rate constant double dagger and our K double dagger equilibrium constant, then what we get is K is equal to K Boltzmann over Planck's constant, K Boltzmann T over Planck's constant, e to the negative delta G double dagger over RT. And that is the essence of where I wanted to get us right now. In other words, what we have done is now set us up to relate rate constant for a fundamental process to the temperature, which appears twice in the equation, and the active free energy of activation. And I want to play with this because this is very powerful. So here's what we're going to play with for the rest of today's lecture. The Eyring Equation. All right. And I find this a very useful tool in thinking about how warming a reaction or cooling a reaction affects the rate. Yes?
Should there be a negative in front of the delta G?
Oh, thank you. Negative delta G. See, organic chemists really are very simple-minded when it comes to that. Thank you. All right. So what I want to do is show you some implications of this in terms of reaction rates with some practical stuff. And the first example, as I said, I wanted to relate this to the homework. It's problem, I think, 4.23. We're not going to put up the problem, but I want to set the background for the problem. So the compound that I'm drawing on the blackboard right now is called AIBN, azo-isobutyronitriol. It's a free radical initiator. That means that when you warm up AIBN, it generates free radicals, compounds with an odd electron, that can start a radical chain mechanism. And the way AIBN works is the bonds break, and you get 2 isobutyronitriol radicals. The dot there means there's a single electron. and 1 molecule of nitrogen, which is very, very stable, and the formation of the nitrogen triple bond, as well as the breaking apart of the molecule to form 3 particles, 3 pieces from 1, drive the reaction. So in sophomore organic chemistry, you learned reaction mechanisms, I think for the most part. No, I take exception. Most of the reaction mechanisms you learned involve moving 2 electrons. But when you studied free radical halogenation, who studied free radical halogenation or free radical polymerization in sophomore organic chemistry? Okay, you learned one more type of mechanism, and we're going to get that on that problem that I referred to, and that's a homolytic cleavage mechanism, where instead of using a 2-headed arrow to show both electrons, or a regular arrow to show both electrons moving, you show a fishhook showing 1 electron goes here, 1 electron goes here, 1 electron goes here, 1 electron goes here, and what you get then are 2 azoisobutyryl nitrile radicals and a nitrogen molecule, where now you have a triple bond between the nitrogens. All right, so what I want to tell you about AIBN is AIBN for this process has a delta G double dagger, an activation energy of 27.2 kilocalories per mole at 298 degrees Kelvin. In other words, at room temperature. And I want to translate this into a rate of reaction using the Eyring equation. So we're just going to plug and chug and get all of our constants in. K, our rate constant, is equal to 1.38 times 10 to the negative 23. That's Boltzmann's constant. If you're good at keeping track of units, it's in joule per Kelvin. And then we're going to take our room temperature, so I'll put this in parentheses to multiply them, and of course we're in Kelvin for room temperature, and I said we're doing this at 298. And then we're going to divide by Planck's constant, which is 6.63 times 10 to the negative 34. If you're keeping track of your units, the units are joule seconds. And then we're going to, in our exponential term, take e to the s negative 27.2 divided by our gas constant. Our gas constant is 0.001987. I always work in kilocalories per mole, and we actually can get away because you notice the joules are canceling out here, so we've got joules here which cancel each other out. I'll use the gas constant in kilocalories per mole. So that's kilocalories per mole Kelvin times 298. All right, so that is a writing out of all the numbers in the Eyring equation. All right, so you take that on through, and you get K, our rate constant, equals 7.0 times 10 to the negative 8th per second for this unimolecular process. So last time we talked about unimolecular kinetics. We talked about half-lives. The half-life is the time of the concentration of a reactant to drop to half the concentration of reactant. If you take the integrated rate equation and you plug in, then for a unimolecular process, I'll say unimolecular reaction half-life T1 half, right, this is like radioactive decay, is equal to log 2. That 2 comes from the factor of 2 as your concentration of reactants drops to a half the concentration of reactants, divided by K, and that works out to 0.693 divided by K. Have you seen that equation in freshman chemistry, maybe? Okay, great. Okay, so I want to translate this to the half-life of the AIBN reagent at room temperature. T1 half is equal to 0.693 divided by 7.0 times 10 to the negative 8 is equal to 9.9 times 10 to the 6th seconds equals 115 days. So what does that mean? That means this initiator reagent is reasonably stable at room temperature. I can have a bottle of it. If I keep it on the shelf, it's going to stick around for a semester or something like that and drop in potency. And we know that cooling things down slows reaction rates. We're going to come to that quantitatively in a moment. But when you buy it, you typically buy it, and it would come on ice, on an ice pack, and you would stick it in the freezer at negative 20 degrees Celsius, which would, for all intents and purposes, shut down that reaction. So in other words, it's stable enough that you can, AIBN is stable enough that you can handle it at room temperature. It's stable enough that you can store it for a long, long time in the freezer. And now, when we use AIBN as an initiator in a free radical reaction, we often carry out this reaction in benzene at 80 degrees Celsius. So at 80 degrees Celsius, 80 degrees Celsius is, of course, 353 Kelvin. If delta G double dagger is still equal to 27.2 kilocalories per mole. And that's good for a first order approximation. In other words, delta G double dagger doesn't change a lot with temperature. I'll show you in a moment the correction that it actually changes. It's about a kilocalorie per mole that it changes. But to a first order approximation, if you're saying, okay, what's temperature doing to this reaction? 80 degrees is refluxing benzene, the temperature at which a free radical chain reaction mechanism like the one in your homework set and like the example that you'll read about is run at 80 degrees Celsius, 353 K. If we plug into the Eyring equation, plug into the half-life equation, we get that K is equal to 1.1 times 10 to the negative 4 per second. In other words, that T1 half is equal to 109 minutes. And that starts to make a heck of a lot of sense. In other words, if you're running this reaction, you want to run the reaction, you go into lab, you set up a reaction, and over the course of some minutes or a few hours, that reaction can occur and progress to the formation of products. In free radical reactions, you run the reaction at a very low concentration of free radical, because if two free radicals meet each other, they combine instantly and they break the chain. So in a free radical chain mechanism, what you want is a trickle of initiation generating free radicals that then carries out a series of propagation steps hundreds of times, generating a molecule of product at each propagation step. You'll see that in your mechanism that you work out. All right, the only thing then I want to go ahead and mention is the fact that actually, as I said, a first order approximation delta G double dagger doesn't change with temperature. Actually, at 80 degrees Celsius, 353 K, the rate constant, the delta G double dagger is equal to 26.4 kilocalories per mole. In other words, and I'll just finish my thought here, that leads to a T1/2 of 35 minutes. So, a little bit of a correction here. But the big picture was room temperature, 100 days, 80 degrees Celsius, minutes. And whether it's 100 minutes or whether it's 35 minutes, doesn't matter. All right, what's this difference coming from? So in the transition state, we are starting to break the molecule apart. In other words, we're on our way, so this is our transition state. We are on our way to forming more particles, three molecules from one molecule. In other words, we have an increase in entropy. And for this reaction, in fact, by observing the difference, the deviation, shall we say, by measuring the half-life, you can calculate delta G double dagger by saying, oh wait, delta G double dagger has changed a little, admittedly only by 0.8 of a kilocalorie per mole. You can now plug into the other equation that you learn, right? I said delta G equals delta H minus T delta S. And in sophomore organic chemistry, you learn that you can apply the same notion with transition states and say delta G double dagger equals delta H double dagger minus T delta S double dagger. And delta H double dagger really, to a second order approximation, doesn't vary with temperature. Delta S double dagger doesn't vary with temperature to a second order approximation. In other words, the variation with temperature in delta G double dagger is coming from this T delta S term. And for this reaction, delta H double dagger is equal to 32 kilocalories per mole. And delta S double dagger is equal to 16 calories per mole K, or entropy units. And delta G double dagger equals delta H double dagger. That means minus T delta S double dagger, right? So that means delta G double dagger equals 32 minus 353 times 0.016, right? I have to keep my units, kilocalories. Kilocalories, that's equal to 26.4. All right, thoughts or questions? Yeah.
Are these just given values, or is there a way to calculate like delta G, double dagger, delta H?
Okay, is there a way? And in fact, the way becomes, you go ahead, you measure the reaction rate at 298 Kelvin. We get that the reaction rate constant, the delta G double dagger, is equal to 27.2. You measure the reaction rate at 80 degrees Celsius. You get that it's 35 minutes. Then you say, okay, what delta H and delta S work out for that. So you basically, now you have a linear equation that over the course of 298 to 253, whatever 25, 80 minus 25 is 55 degrees. So over the course of 55 degrees, we have a change in reaction energy, in activation energy, a decrease of 0.8 kilocalories per mole, and then that gives you 0.16 as the EU.
So these were just like experimental?
Exactly, experimentally. But coming back, if we didn't know these activation parameters, 27.2 would be a pretty good guess. I mean, we could have rounded both of them practically to 27 and said, that's pretty good. So to a first order approximation, if you know delta H double dagger, delta G double dagger, or know a rate constant at one temperature, you can bootstrap yourself by way of the Eyring equation to the rate at another temperature. And that's pretty powerful. And in most cases, this is an example of a reasonably large change in entropy, 16 EU, not super high, but higher than average. For many processes, delta S double dagger is a lot less than 16 entropy units, and so the corrections become even smaller. All right, other questions? These are good, these are important. So I, in particular, like NMR spectroscopy, and I want to give you two examples from NMR that I think are fun. We'll come to NMR in chapter 10 here. All right, so I want to talk about the NMR timescale and talk about what's fast and what's slow on the NMR timescale. NMR is one of the tools that people often use to study rates of various processes. And so we'll take as an example, well, first let's talk about the NMR timescale. What did I do with my pen? There we go. So, if I wanted to give a quick and sort of easy summary, I'd say processes that occur with lifetimes of less than about 10 to the negative 2 seconds, less than about 10 milliseconds, are what we would call fast. And processes at seconds. And processes that occur with, say, less than 10, with greater than 10 to the negative 1 second are slow. In other words, a motion conformational interconversion that takes a millisecond to occur is fast on the NMR timescale and is invisible. A motion that takes a second to occur is slow on the NMR timescale and is visible. So let's take a look at the molecule cyclohexane. Right, we like cyclohexane. We've been using it as an archetype for conformational analysis and for transition states. So cyclohexane shows one line in the NMR at room temperature. All right, here's cyclohexane. And I'm only going to draw one axial proton and one equatorial proton. So cyclohexane has two different types of hydrogens. It has hydrogens in the axial environment, hydrogens in the equatorial environment. They shouldn't show up in the same position in NMR. And yet we see only one line. And the reason for that is these two hydrogens swap positions. Cyclohexane undergoes ring flip. And in ring flip, the hydrogen that was axial becomes equatorial, and the hydrogen that was equatorial becomes axial. And this process occurs quickly on the NMR timescale. How quickly? Well, what's the energy barrier? If you go back to freshman chemistry, you probably in about chapter 4 of sophomore chemistry, in about chapter 4 of your textbook, learned about cycloalkanes. It might have been chapter 5. You probably first learned about ethane and butane and eclipsed and staggered and bond rotations. Then you probably learned about the cyclohexane ring, and you learned that the cyclohexane is a chair conformation, and that the chair conformation can undergo a ring flip. It goes by way of a boat transition state or a twist boat intermediate. You then eventually, after going through a couple of one boat, then one twist boat, then another twist boat, then another boat, then back to the other chair, it flips. The overall barrier for this process, delta G double dagger, is about 12 kilocalories per mole, depending on the source you look at, 10 to 12 kilocalories per mole, but the source I use said 12 kilocalories per mole. We plug and chug into the Eyring equation. That leads to a K, right, it's a unimolecular process, of 9.8 times 10 to the negative 3 per second at 298 K. That means we have a T1/2. I'm just repeating all the calculations that I did on the first couple of blackboards when I introduced this, equals 7.1 times 10 to the negative 5th seconds, or 71 microseconds, and that is fast. So a conformational process that has a barrier of 12 kilocalories per mole, of course, it's very fast on the laboratory time scale. It's also fast on the NMR time scale. Now, I'll juxtapose cyclohexane with another classic example that's often used when talking about rates in NMR processes, and that is the molecule DMF, dimethylformamide. Dimethylformamide shows two methyl lines, in the NMR spectrum at room temperature. So in other words, if you look at, in proton NMR, about 3 parts per million, you'll see a methyl peak and another methyl peak. So this would be at room temperature. This would be about 3 parts per million, somewhere around here in the NMRs. All right, so what's going on here? Dimethylformamide is the dimethylamide of formic acid. The amide group is planar. You have resonance. You have partial double bond character. The nitrogen, unlike an amine, is not pyramidal. It's donating its lone pair into the carbonyl. You can write a second resonance structure that illustrates it. And that nitrogen then is sp2 hybridized, not sp3 hybridized. So you have one methyl group that's on the same side as the carbonyl group, one methyl group that's on the opposite side. Those two methyl groups don't swap places rapidly on the NMR timescale, so you see them as two sets of lines. In other words, this reaction is slow, and I'll use the same notation I used for cyclohexane to show the swapping I'll put a star on one methyl group, and I'll just show it swap into the other position. Delta G double dagger, for this process, the free energy of activation is about 21 kilocalorie per mole. And that, when you take that through, that leads to a K equals 2.5 times 10 to the negative 3 per second at 298 K. And that means you have a half-life, T 1/2 is equal to 280 seconds. So that's slow, and we contrast 71 microseconds as fast. So, one of the classic demonstrations of what's called dynamic NMR, how NMR spectra change with temperature, how groups interconvert or swap places, is heating up the spectrum, heating up a sample of DMF. And if you heat it up to 120 degrees Celsius, the peaks start to broaden and become fat. And if you heat it up more to 160 degrees Celsius, you see a single peak. In other words, we go from the DMF situation to the cyclohexane situation. In other words, here we're slow at room temperature. At 160 degrees, we're fast. And you can apply the Eyring equation and see exactly what this means. At 160 degrees Celsius, that's 433 K. Our rate constant equals 230 per second, and that translates to a T 1/2 is equal to 0.003 seconds. That's 3 milliseconds, and that's fast. Remember, we said 10 milliseconds is slow on the NMR. Above 100 milliseconds is slow on the NMR timescale. Below 10 milliseconds is fast on the NMR timescale. And of course, if you do this experiment and find the exact temperature of coalescence, you can figure out, because there's a relationship between peak width, in other words, the exact point where these sort of merge into one peak, there's a relationship between peak width and rate constant based on the uncertainty principle. You can, from NMR spectroscopy, get delta G double dagger per process.
I was going to ask which NMR is that?
Typically one would do this example with proton NMR. And the key factor here is actually when we come to the uncertainty principle, because line width basically relates to lifetime, and in turn that relates to coalescence, relates to separation. It's the separation in hertz. So the difference, we've been looking at huge effects in rate. The difference in hertz between carbon NMR and proton NMR is a factor of 4. In other words, 1 ppm at 300 megahertz proton NMR is 300 hertz. 1 ppm at 75 megahertz carbon NMR, which is the same magnet, just the frequency tuned for carbon, is 75 hertz. Now in practice, these two lines are going to be a few tenths of a ppm apart in proton NMR, a few ppm apart or ppm or so apart in carbon NMR. And so it's going to be almost a wash. I mean, we're talking a few degrees difference here in coalescence.
So I'm just a little bit confused on what the half-life represents in this example, because you're not really having like a decrease in concentration, is that like the average?
Okay,
time
imagine
either
for a moment.
concentration?
Imagine this, think of this as a thought experiment. Imagine for a moment I could say put a CD3 group here, put some sort of label here, and somehow make that molecule in form where it had the methyl group here. The half-life would be the time for half of those molecules to go to having the methyl group over here. So it is the half-life of rotation. It is basically, if I have 100 molecules, it's the time in which half of those molecules will flip. Of course, some of them will flip back in that time, but if I lined up 100 molecules and could watch them and say, oh, I saw you flip, I saw you flip, I didn't see you flip, didn't see you flip, saw you flip, half of them would have been seen to flip.
Since it's an equilibrium though,
They'll
would
also flip back, yeah.
all of them, so like the concentration will never,
The concentration doesn't
Right, okay.
change. But from the point of view of NMR, you have to have this methyl group stay here for basically more than 100 milliseconds, shall we say, in order to see it as a reasonably sharp line, separate from this line. Other questions? These are good. These are important. I want to do a few things. I generally calibrate myself, and often I'll do that just by running some calculations. And I want to show you my thinking, and I hope I lend clarity, not confusion, in the next two tables that I want to present, because what I want to do is present the way I like to think about effects and sort of calibrate myself. And so the first thing I'll do, I made a table of the effect of delta G double dagger on half-life based on what we were talking about, and I just took at 298K as an example. So delta G double dagger, this is all calculated from basically, okay, how does delta G double dagger translate into rate constant? And what I wanted to do in my own mind was sort of window 5-degree increments. So I said, let's look at 10 degrees, 15 degrees, 20 degrees, and 25 10 kilocalorie per mole, so a process with a lower barrier than cyclohexane ring flip, 15 kilocalories per mole, 20 kilocalories per mole, a process like DMF rotation, and 25 kilocalories per mole, a process kind of akin to AIBN decomposition. And I just wanted to calibrate myself on T1/2 in seconds at 298K. And we get 2.4 times 10 to the negative 6 seconds, or 2.4 microseconds. In other words, a process with a 10 kilocalorie per mole barrier occurs very fast. We get, for 15, 0.011, in other words, 11 milliseconds. We go up to 20, we get 52 seconds, and we go to 25 kilocalories, we get 2.4 times 10 to the 5th seconds, or 67 hours. In other words, as we're moving in these 5 kilocalorie per mole increments, we're shifting about 3 orders of magnitude. So in my mind's calibration, we're talking roughly 3 orders of magnitude and that calibration makes a heck of a lot of sense, right? Because negative 1.36 kilocalories per mole difference at 298K leads to a 10x faster reaction, right? It's 10x in equilibrium constant, 10x in rate constant. And so when I, thinking just in round numbers, am moving myself through 3 orders of magnitude, I'm moving myself through slightly more than 3 times 1.36 kilocalories per mole. In other words, that's 4.7, and I'm saying 5. So basically, 5 kilocalories per mole leads to 3 orders of magnitude faster rate. That's a nice calibration point to hold in your head. The other one, and I want to finish up quickly because we're at the end of our time and I want to relate this to something useful. So I did the same thing for effect of temperature on the half-life of a reaction. And I just took a reaction with delta G double dagger equals 20 kilocalories per mole. And I just wanted again to see what's the effective temperature to calibrate myself. So I took 223 Kelvin. I took 223 Kelvin because that's negative 50 degrees Celsius. It's a lousy 2. I took 298 Kelvin because we always use 298 Kelvin, that's 25 degrees Celsius. And I took 373 degrees Kelvin, 100 degrees Celsius. This might be represent a range of temperatures at which you could run a reaction. A little bit above dry ice temperature, room temperature, boiling water. And I calculated again, T1 half. We get 6 times 10 to the 6th, 52, and 0.047 seconds. In other words, basically 50 degrees, as we saw with the AIBN reaction, makes a heck of a big factor. Okay, what's the take-home message on this? Take-home message, when you're running a reaction, becomes a 10 degrees Celsius increase if it goes to, say, about a 2 to 3 faster rate, which is probably something you learned in biology, in enzyme kinetics. Warming a reaction up by 10 degrees leads to it occurring about 2 or 3 times faster. And I think at this point, I probably have run to the end of my time. There's one question?